Welcome to Chapter 1 of Calculus and Vector Analysis, Fundamentals of Differentiation and Numerical Differentiation. The subtitle says where we are going, the instantaneous rate of change, and how to compute it from data. Differentiation is the first of the two operations this whole series is built from, and it earns that position because it answers a question that comes up everywhere. Given a quantity that varies, how fast is it varying right now? In materials science, that appears as the rate of change of a physical property with respect to temperature. In process engineering, it appears as a reaction rate. In machine learning, it appears as the gradient of a loss function. We will start from the definition as a limit, collect the differentiation rules, and then spend most of our time on the part that a textbook often skips: what to do when you have no formula at all, only a column of measured numbers. Here is the definition. The derivative of a function f at the point x equals is the limit, as h goes to 0, of f of a plus h minus f of a, all divided by h. Read the pieces one at a time. The numerator is the change in the function value between 2 points that are a distance h apart. The denominator is the change in the input. Their ratio is the average rate of change over that interval, which geometrically is the slope of the secant line joining the 2 points on the curve. The limit is what makes it a derivative rather than an average. As h shrinks toward 0, the second point slides back toward the first, the secant line pivots, and in the limit it becomes the tangent line at the point A, f of a, so the derivative is the slope of that tangent line. That single number is what every application in this chapter ultimately asks for. Let us make that concrete with the simplest interesting example. Take f of x equals x squared and ask for the derivative at x equals 2. The function value there is 4, so the point on the curve is 2, 4. The derivative of x squared is 2x, which at x equals 2 gives 4. So the tangent line at that point has slope 4, and you can see it on the plot. It touches the parabola at exactly one place and leans at the same angle the curve does there. Notice what the derivative is and is not. It is not a curve, and it is not a description of the whole function. It is one number attached to one point, the slope of the line that just touches the curve there. Move to a different point, and you get a different number. Collecting those numbers for every point is what turns the derivative at a point into the derivative function. Now the practical version. If you cannot take the limit symbolically, take it approximately. Pick a small but finite h and evaluate the same quotient. That is the forward difference method, and the code is a single line. F of x plus h minus f of x divided by h, run it on x squared at x equals 2 with h set to 10 to the minus 5, and the numerical derivative comes out as 4.000010 against the analytical answer of 4.000000 for an error of 1 times 10 to the minus 5. Two things are worth noticing. First, the recipe never needed a formula for the derivative, only the ability to evaluate f, which is exactly the situation you are in with a simulation or an experiment. Second, look at the size of the error. It came out the same order as h itself, and that is not a coincidence. Before going further into numerics, let us collect the rules you already need. They come in two families. The first is the derivatives of the elementary functions. A constant differentiates to 0, x to the n differentiates to n times x to the n minus 1, e to the x is its own derivative, the natural logarithm of x differentiates to 1 over x, sine differentiates to cosine, and cosine differentiates to minus sine. The second family is the combination rules that let you build up from those pieces. A constant multiple pulls straight out. The derivative of a sum is the sum of the derivatives. The product rule gives f prime g plus fg prime, and the quotient rule gives f prime g minus fg prime, all over g squared. These basic formulas and combination rules cover most of the derivatives you will meet in this chapter. Later chapters add further tools, most importantly the chain rule for composed functions. Memorizing them is worth the afternoon it costs, because they turn up in every chapter that follows. You do not have to apply those rules by hand. SimPy applies them symbolically. Define a symbol x, hand an expression to simpy.diff, and it returns another expression rather than a number. The output shows the rules at work. X cubed becomes 3x squared, the power rule. The exponential of x comes back as itself. The logarithm of x becomes 1 over x. Sine becomes cosine. Then the interesting ones. X squared times the exponential of x becomes x squared times the exponential of x plus 2x times the exponential of x, which is the product rule. And sine of x over x becomes cosine of x over x minus sine of x over x squared, which is the quotient rule. One caution about reading such output. SimPy print sums in its own canonical order, so the exact term order may differ between versions. Two printings that look different can be the same expression. In real data analysis, the functional form is often unknown, so numerical differentiation becomes necessary, and there are three representative ways to form the difference quotient. The forward difference looks ahead. F at x plus h minus f at x. Over h, the backward difference looks behind. F at x minus f at x minus h. Over h, the central difference looks both ways. F at x plus h minus f at x minus h. Over 2h, the forward and backward formulas are accurate to order h, the central formula is accurate to order h squared, which is a genuinely different quality of answer. The reason is worth holding on to. Each one-sided estimate carries a leading error term proportional to h, and the two one-sided errors are equal in size and opposite in sign. Averaging the two directions, which is exactly what the central formula does, cancels that leading term and leaves the smaller one behind. Order h and order h squared sound like small print, so let us translate them into something you can feel. An order h error means that if you have the step, you roughly have the error. An order h squared error means that if you have the step, you roughly quarter it. Over several halvings, that gap compounds fast. The standard way to see this is a log-log plot of absolute error against step size, because on logarithmic axes, a power law becomes a straight line and the exponent becomes the slope. In the range where truncation error dominates, an order h error plots as a line of slope 1 and an order h squared error as a line of slope 2, so the two methods separate visibly as the step shrinks. The reference lines on the right show those two slopes. When you measure the error of your own difference formula and plot it this way, the slope you get is a direct check that you implemented the formula you meant to. One warning before you take that picture too literally: the straight lines do not continue forever. For very small h, floating point roundoff takes over and the measured error stops falling. The next slide shows what that looks like and where the turning point sits. There's a limit to how far you can push the step down, and it is better to know it in advance than to meet it by accident. Every function value a computer returns carries a relative error of about machine epsilon, which in double precision is roughly 2 times 10 to the minus 16. When h is very small, f at x plus h and f at x agree in almost all of their digits, so the subtraction cancels those digits, and what is left is mostly rounding noise. Dividing that noise by a tiny h magnifies it. So the total error has two competing parts: truncation error, which falls as h shrinks, and roundoff error, which grows as h shrinks. Their sum is the U-shaped curve on the right, and it is measured rather than sketched. Differentiating the sine function in double precision, the forward difference bottoms out near h equal to 10 to the minus 8, close to the square root of epsilon, at an error around 6 times 10 to the minus 9. The central difference bottoms out near h equal to 6 times 10 to the minus 6, close to the cube root of epsilon, at an error around 4 times 10 to the minus 12. Below those steps, smaller is strictly worse. Here is the point that decides which method you should actually reach for. You might expect the more accurate central formula to cost more, since it mentions 2 shifted points. It does not. As implemented here, all 3 methods evaluate f exactly twice per derivative, so the cost is the same. Forward evaluates f at x plus h and at x. Backward evaluates f at x and at x minus h. Central evaluates f at x plus h and at x minus h 2 evaluations each, and one of them buys you an extra order of accuracy for free. Central difference is therefore the default choice unless f can only be sampled on one side of x, which does happen at the edge of a dataset or at the start of a time series. There is one caveat worth stating honestly. Central difference costs one extra evaluation when f of x is already known and could have been reused, as inside a Newton iteration. Differentiating a derivative gives a higher-order derivative, and each order tells you about a different feature of the shape. The first derivative gives the slope. The second derivative f double prime characterizes the convexity of the function, whether it curves upward or downward. Third and higher-order derivatives characterize finer shape details. Numerically, each order gets its own stencil. The second derivative is approximated by f at x plus h minus 2f at x plus f at x minus h all over h squared, which is a symmetric three-point pattern. The third derivative needs 4 points and a wider reach. A clean way to test any such stencil is a function whose derivatives you know exactly. For f of x equals x to the fourth at x equals 2, the exact first, second, and third derivatives are 32, 48, and 48. So any implementation error shows up immediately as a mismatch against those three numbers. Here is what all of this is for. The thermal expansion coefficient alpha of a material is defined as the rate of change of length L with respect to temperature T, normalized by the length itself. Alpha equals 1 over L times dL by dt. Notice that the definition is a derivative, and that in laboratory work the starting point is often not an explicit formula, but a table. A column of temperatures and a column of measured lengths, in this case running from 300 Kelvin up to 600 Kelvin. So the procedure is exactly the one we have been building. Fit a smooth cubic spline through the measured points so that you have something differentiable. Differentiate that spline to obtain dL by dt at each temperature, and then divide by the measured length to get alpha. The temperature dependence of alpha then falls out as a curve from data that started as 7 measured temperature length pairs. There is one more idea worth carrying forward, because it is cheap and it generalizes. Richardson extrapolation is a technique that combines numerical differentiation results at different step sizes to obtain more accurate approximations. Concretely, take a central difference at step h and call it d1, take another central difference at step h over 2 and call it d2, then form 4d2 minus d1, all divided by 3. Why that particular combination? Because we know the central difference carries a leading error proportional to h squared. Having the step divides that leading term by 4, so the weights 4 and minus 1 over 3 are chosen precisely, so the h squared terms cancel between the two estimates. What survives is the next term in the expansion, of order h to the fourth. So two order h squared estimates are combined algebraically into one of order h to the fourth, at the cost of evaluating the central difference at 2 step sizes. 4 function evaluations rather than 2. That is a very cheap way to buy 2 extra orders of accuracy. Let us pull the chapter together. A derivative is the instantaneous rate of change of a function, and geometrically it is the slope of the tangent line at a point, defined as the limit of a difference quotient. When you have a formula, symbolic differentiation with sim pi applies the rules for you. When you have only data or a black box function, numerical differentiation applies them approximately. Among the basic difference formulas, the central difference has order h squared accuracy against order h for the forward and backward methods, at the same 2 function evaluations, which makes it the default unless you can only sample on one side. Shrinking the step does not help forever, though. Below roughly 10 to the minus 8 for the forward difference, and 6 times 10 to the minus 6 for the central difference, floating point round-off dominates, and the error starts climbing again. Higher-order derivatives get their own symmetric stencils, and a known test function is the fastest way to check them. Richardson extrapolation enables even higher precision numerical differentiation by combining 2-step sizes. Next chapter, the fundamentals of integration and numerical integration, from Riemann sums to the trapezoidal and Simpson rules, and on to heat calculations. Welcome to Chapter 2 of Calculus and Vector Analysis, Fundamentals of Integration and Numerical Integration. Last chapter, we took functions apart, asking how fast a quantity changes at an instant. This chapter puts them back together. Integration is the operation that calculates accumulated quantities, not how fast, but how much in total. In materials science, it is used for heat calculations, in process engineering for the total amount of reactants consumed, and in machine learning for the normalization constants of probability distributions. The plan mirrors the previous chapter. We start with the definition, which turns out to be a limit of sums rather than a limit of quotients. We meet the theorem that connects integration back to differentiation. And then we spend most of the time on numerical methods, because they are what you reach for when only sampled values are available, or when an antiderivative is hard to find on paper. Here is the definition. The definite integral of f over the interval from a to b is the limit, as n goes to infinity, of the sum from I equals 1 to n of f evaluated at a sample point xi star, times delta x read the construction. Cut the interval into n pieces, each of width delta x in each piece, pick a sample point, and evaluate f there. Multiply that height by the width to get the area of a thin rectangle, add up all n of them, and then let n grow without bound. Now one caution that a hurried reading always loses. Geometrically, the integral represents the signed area between the curve and the x-axis. Parts of the curve above the axis contribute positively, parts below the axis contribute negatively. Only when f of x is greater than or equal to 0 on the whole interval does the definite integral coincide with the ordinary unsigned area. The definition says pick a sample point in each strip, but it does not say where. 3 choices are standard: the left endpoint, the right endpoint, and the midpoint of each strip. On the plot, you can see the midpoint version for f of x equals x squared on the interval from 0 to 1, with 10 strips. Each rectangle stands on one strip, and its height is the function value at the center of that strip. Notice that the rectangle tops cross the curve rather than sitting entirely above or below it, so the overshoot on one side of the midpoint partly cancels the undershoot on the other. That is why the midpoint rule usually does better than the 2 endpoint rules at the same number of strips. As the strips get thinner, all 3 choices converge to the same limit, which is exactly what makes the definition well posed. Now the theorem that saves us from ever having to compute that limit by hand. If f is a continuous function and capital F is an antiderivative of f, meaning a function whose derivative is f, then the definite integral of f from a to b equals f of b minus f of a. Look at what just happened. On the left is a limit of infinitely many sums. On the right is a single subtraction of 2 numbers. The whole construction collapses, provided you can find the antiderivative. And the theorem carries a second message, which is why it is called fundamental. It shows that differentiation and integration are inverse operations of each other. The 2 chapters we are building are not 2 separate subjects, but 2 directions along the same road. Note the hypothesis, though. Continuity of f and the existence of an antiderivative are what make the collapse legal. Finding the antiderivative by hand is a craft, and SimPy has absorbed most of it. Hand an expression to simpy. Integrate together with the variable, and you get back an indefinite integral. X squared gives x cubed over 3, the exponential of x gives itself, sine gives minus cosine, 1 over x gives the logarithm, and x times the exponential of x gives x minus 1. All times the exponential of x. Each of these is an antiderivative, so a constant of integration is understood in every case. Add a pair of limits as a tuple, and the same call returns a definite integral instead. The integral of x squared from 0 to 1 comes back as 1/3, and the integral of sine from 0 to pi comes back as 2. Notice the shape of that second call. It is the fundamental theorem in software. Find the antiderivative, then evaluate it at the 2 limits and subtract. But not every integrand has an antiderivative you can write down, and measured data has no formula at all. So we go numerical. The trapezoidal rule is the most basic numerical integration method. It approximates the curve with straight lines and calculates the resulting area. Concretely, sample f at n plus 1 equally spaced points, join neighboring samples with straight segments, and add up the areas of the trapezoids underneath. Written out, the rule is h times the quantity. Half of the first sample, plus every interior sample at full weight, plus half of the last sample, where h is the width of one strip. Those half weights at the two ends are the fingerprint of the method, and forgetting them is the classic implementation bug. The accuracy is of order h squared, so having the strip width cuts the error by roughly a factor of 4. Simpson's rule buys accuracy by upgrading the shape of the approximation. Instead of joining neighboring samples with straight lines, it fits a parabola through each consecutive triple of samples, so a curved integrand is matched by something curved. Working out the algebra gives a memorable weight pattern. h over 3 times the first sample, plus 4 times the second, plus 2 times the third, alternating 4 and 2 through the interior, and finishing with the last sample at weight 1. Because each parabola spans 2 strips, and adjacent triples share an endpoint rather than a midpoint, the number of strips n must be even, and a good implementation raises an error rather than silently producing nonsense when it is not. The payoff is accuracy of order h to the fourth, against order h squared for the trapezoidal rule for the same sample points. Let us translate those orders into something practical. For the trapezoidal rule, the error falls like 1 over n squared, so multiplying the number of strips by 10 cuts the error by roughly a factor of 100. For Simpson's rule, the error falls like 1 over n to the fourth, so the same tenfold increase cuts it by roughly a factor of 10,000. That is 2 extra orders of magnitude per decade, and over the range of n, you would actually use it as a gap of many decimal places rather than a marginal improvement. As in the previous chapter, log-log axes are the natural place to see this. A power law becomes a straight line, and the two rules appear as lines of slope -2 and -4. If you plot your own measured error and the slope is wrong, treat that as a reason to investigate rather than as a verdict on the mathematics. Check the implementation first, then the range of n you tested, the smoothness of the integrand, the accuracy of your reference value, and whether roundoff has begun to matter. In production, you rarely write these rules yourself. The SciPy library provides high-performance integration functions with adaptive step, size adjustment, and high-order quadrature methods. Take an oscillating integrand, sine of x times the exponential of -x over 10, on the interval from 0 to 20. Because a closed-form antiderivative exists for it, we have an analytical reference value of 0.92318488794, and that matters. The reference is an analytical result, not another numerical one, so the comparison is a real test. The adaptive routine quad returns that value with a true error of 2.22 times 10 to the -16. Fixed-order Gauss-Legendre quadrature with 50 nodes gives 8.88 times 10 to the -16. Ramerg integration on 2 to the 10th plus 1 equally spaced samples returns 0 error at printed precision. All three are essentially at machine precision. Here is the application. The amount of heat Q required to heat a substance from temperature T1 to T2 is obtained by integrating the heat capacity Cp of T with respect to temperature. If the heat capacity were a constant, you could just multiply, but it is not. For copper, it rises measurably with temperature, so the answer is an integral rather than a product. The model used here is a Mayer-Kelly type linear fit, 22.64 plus 6.28 times 10 to the -3 times T in joules per mole Kelvin, and it is stated as valid near 300 to 600 Kelvin. Note what it is not. This is not the Chamate equation, which uses a scaled temperature and a different functional form. Integrating this fit from 300 to 600 Kelvin gives 7,639.80 joules per mole. Now the part worth slowing down for, because it is a habit rather than a formula. The numerical integration and the analytical integration of that same fitted expression agree to 7,639.80 joules per mole, with a difference of 0. It is tempting to read that as confirmation that the answer is right. It is not. Both sides integrated the same model, so their agreement proves only that the quadrature was implemented correctly. The physical question is separate. How good is the model? Integrating the full tabulated Chamate expression for solid copper over the same interval gives 7,681.83 joules per mole, so this linear fit is about 0.55% low. As the source puts it, that is accurate enough to illustrate the method, but not a substitute for the tabulated thermochemical data. One last practical topic. Special care is needed when the integrand diverges to infinity at some point, which is called a singularity, or when the integration interval itself is infinite, which makes the integral improper. Two standard examples make the point. The integral of the exponential of minus x squared from 0 to infinity has an unbounded interval, and its value is the square root of pi over 2. The integral of 1 over the square root of x from 0 to 1 has a bounded interval, but an integrand that blows up at the left endpoint, and its value is exactly 2. Both can be computed numerically with appropriate methods. An adaptive routine will accept infinity as a limit and transform the interval internally. And when you know where the singular point is, telling the routine explicitly helps it place its sample points sensibly rather than discovering the trouble by accident. Let us pull the chapter together. A definite integral is the signed area between a curve and the axis, defined as a limit of Riemann sums, and it is the tool for accumulated quantities. The fundamental theorem collapses that limit into a subtraction of antiderivative values, and it is what makes differentiation and integration inverse operations. Among the basic numerical methods, the trapezoidal rule has order h squared accuracy and Simpson's rule order h to the fourth, and the psi-pi quad function achieves high-precision integration through adaptive step size adjustment. Improper integrals and integrals with singularities can also be handled numerically with appropriate methods. And the heat calculation carried a lesson beyond calculus. When a numerical result agrees with an analytical one, check whether they came from the same model before calling it validated. Next chapter, multivariable calculus, where functions depend on several variables at once and a single derivative becomes a whole vector. Welcome to Chapter 3 of Calculus and Vector Analysis, Multivariable Calculus. So far, every function has taken one number in and given one number out, and its derivative has been a single slope. Real problems are rarely that obliging. A property depends on temperature and pressure and composition at once. A loss function depends on millions of parameters at once. So we generalize. The generalization is more interesting than it first looks, because once a function has several inputs, the question how fast is it changing needs a follow-up question. Changing in which direction? That single observation organizes the whole chapter. We will start with partial derivatives, which answer the question one axis at a time, then assemble them into the total differential and the chain rule, then into the gradient, and finally turn the machinery around to integrate over regions rather than intervals. The simplest way to differentiate a function of several variables is to refuse, temporarily, to treat it as one. The partial derivative of f with respect to x is the limit, as h goes to 0, of f at x plus h and y, minus f at x and y, all over h. Compare it with the definition from Chapter 1, and you will see it is the same difference quotient. The only new thing is what is not moving. Y appears in both function evaluations and is never perturbed. So you differentiate with respect to one variable while keeping the other variables fixed, and the curly d symbol in the notation is there precisely to remind you of that. Practically, it means every rule you already know still applies. Treat y as though it were a constant, differentiate in x as usual, and you are done. Take f of x and y equal to x squared plus xy plus y squared, and evaluate its partial derivatives at the point 1, 2. Analytically, differentiating in x treats y as a constant, so x squared gives 2x, xy gives y, and y squared gives nothing. That is 2x plus y, which at the point 1, 2 equals 4. Differentiating in y by the same logic gives x plus 2y, which equals 5. Numerically, we use exactly the tool from Chapter 1. A central difference, but taken along one axis. Perturb x by plus and minus h with y fixed, divide by 2h, and the result matches 4. Perturb y the same way, and the result matches 5. Nothing conceptually new has been introduced. A partial derivative is a single variable derivative taken along a chosen axis. SymPy handles the symbolic side with the same function we used before. Declare several symbols at once, then call simpy.diff with the expression and the variable you want. Take f equal to x squared y plus y squared z plus z squared x, a three-variable example where every variable appears in two of the three terms. Differentiating with respect to x gives 2xy plus z squared. The middle term vanished because it contains no x with respect to y. We get x squared plus 2yz, and with respect to z, we get 2xz plus y squared. The pattern is worth naming. Every term that does not contain the chosen variable differentiates to 0. One small software caution from the source code. The set of free symbols has no guaranteed iteration order, so the example sorts them before printing, which keeps the output reproducible between runs. Now the concept the rest of the chapter leans on. A partial derivative measures the change of f along one axis only, but in many real applications, several variables change at once. When they do, the first-order change of f is the total differential. df equals the partial of f with respect to x times dx, plus the partial with respect to y times dy. Read it as a budget. Each variable contributes its own displacement multiplied by the sensitivity of f in that direction, and the contributions simply add. Formally, this is the linear approximation of delta f, the difference between f at the displaced point and f at the original point. It is an approximation, and the source is precise about what is dropped. The neglected part is of second order in delta x and delta y, so, for a sufficiently smooth function, the estimate generally improves as the displacement gets smaller. But how good it is at any particular step depends on the function's higher-order behavior. An affine function has no second-order part at all, so its linear estimate is exact even for large steps. Let us put a number on that. Stay with f equal to x squared plus xy plus y squared at the point 1, 2, where the partial derivatives are 4 and 5. Take a small step, dx of 0.01 and dy of minus 0.02. The total differential predicts 4 times 0.01 plus 5 times minus 0.02, which is minus 0.060000. The actual change, computed by evaluating f at both points and subtracting, is minus 0.059700. The difference is 3 times 10 to the minus 4. The plot shows what happens if you keep stepping in the same direction. The straight line is the total differential, and the curve is the truth, and the gap between them opens up in proportion to the square of the step, exactly as the second-order remainder predicts. Now suppose the variables are not free, but are themselves functions of some parameter t, so that x equals x of t and y equals y of t, then moving t traces out a path through the plane, and f varies along that path. Dividing the total differential through by dt gives the chain rule for multivariable functions. df by dt equals the partial of f with respect to x times dx by dt, plus the partial with respect to y times dy by dt. Look at what it does. It converts a question about a multivariable function into a single ordinary derivative along a curve. This is the rule that lets you differentiate along a path through a scalar field, which is exactly what line integrals in Chapter 5 rely on, and it is also the rule that backpropagation in neural networks is built from. A rule this important deserves a test that could actually fail. Keep the same f, and let the path be the unit circle. X equals cosine of t, y equals sine of t. The chain rule root assembles the answer from pieces. 2x plus y times minus sine of t, plus x plus 2y times cosine of t. The independent root ignores the chain rule entirely and takes a central difference of the composed function directly in t, with a step of 10 to the minus 6. At t equal to 0.7, the chain rule gives 0.169967, and the direct central difference gives 0.169967. They agree to 6 decimal places, and this is a genuine test rather than a restatement, because the two computations take independent differentiation roots. One combines the partial derivatives with the path velocities, while the other never forms a partial derivative at all and simply applies a central difference to the composed function. Once you have the partial derivatives, it is natural to stop treating them as a list and start treating them as a vector. The gradient of a scalar field f is the vector whose components are the partial derivatives with respect to each coordinate, written with the nabla symbol. Two things change when you make that move. First, the notation compresses. The total differential becomes the dot product of the gradient with the displacement. Second, and more importantly, a direction appears. Among all infinitesimal steps of a fixed length, the gradient vector points in the direction of steepest increase of the function, and its length measures how steep that increase is. That geometric fact is what makes it the engine of optimization. If the gradient points the locally steepest way up, then its negative points the locally steepest way down, and taking repeated small steps in that direction is the whole idea behind gradient descent. The algorithm is 3 lines long. Evaluate the gradient at the current point, step a small distance in the opposite direction, and repeat. The step size is the learning rate. Watch it on the simplest possible bowl, f equal to x squared plus y squared, starting at the point 3, 2 with a learning rate of 0.2. The gradient there is 2x, 2y, so each update multiplies both coordinates by the same factor, which is why the path on the plot is a straight ray heading for the minimum at the origin rather than a curve. Notice also how the steps shrink as the path approaches the bottom. Near the minimum, the gradient itself is small, so the algorithm naturally slows down. On a harder landscape, the path would bend, wander along valleys, and depend heavily on the learning rate, but this is the mechanism underneath. Real optimization problems usually come with strings attached. Minimize the cost, but hold the total mass fixed. The Lagrange multiplier method handles that. The problem of optimizing f of x and y under the constraint g of x and y equal to 0 is reduced to finding the stationary points of the Lagrange function L, defined as f minus lambda times g, where lambda is the multiplier. The constraint has been absorbed into the objective, so an unconstrained stationary point search now solves a constrained problem. Take the standard illustration. Minimize x squared plus y squared subject to x plus y equal to 1. Geometrically, you are looking for the point on a straight line that is closest to the origin, and by symmetry, that is the midpoint. The analytical solution is x equals y equals 0.5, giving a minimum value of 0.5, and a numerical optimizer reproduces it. Now we run the chapter in the other direction and generalize integration. In Chapter 2, we accumulated over an interval by cutting it into strips. Here we accumulate over a two-dimensional region by cutting it into small patches, multiplying each patch area by the function value there, adding them up, and refining the grid. The result is a double integral. In practice, it is evaluated as an iterated integral. Integrate with respect to one variable while treating the other as a constant, then integrate the result with respect to the second. Take the integral of x times y over the rectangle, where x runs from 0 to 1 and y runs from 0 to 2. Because the integrand factors, the answer factors too. The x part contributes 1/2 and the y part contributes 2, so the value is 1.0, and a numerical double integration routine agrees. Rectangular regions are easy. Round regions are not, because the limits of the inner integral start depending on the outer variable. The cure is to change coordinates. Write x as r cosine theta and y as r sine theta, and a disk becomes a rectangle in the new variables, with r running from 0 to the radius and theta running from 0 to 2 pi. But you cannot simply swap the symbols. The area element transforms as well. Dx dy becomes r, dr, d theta, and that extra factor of r is the Jacobian. Forgetting it is the classic error. Take the integral of x squared plus y squared over the unit disk. In polar form, the integrand r squared times the Jacobian r gives r cubed, and the integral evaluates to pi over 2, approximately 1.570796. A numerical evaluation matches it to about 2 times 10 to the minus 16. Here is the application, and it comes with a unit lesson. On a circular silicon wafer of radius 5 centimeters, an implanted impurity is distributed with a dose that falls off with distance from the center, peaking at 1 times 10 to the 15 at the middle. The quantity being integrated is an areal density, in atoms per square centimeter, so integrating it over an area in square centimeters gives a pure count of atoms. Had it been a volumetric concentration in atoms per cubic centimeter, the same integral would have left units of atoms per centimeter, a sign that something has gone wrong. Doing the integral in polar coordinates, remembering the factor r, gives a total of 4.9647 times 10 to the 16 atoms, and dividing by the wafer area gives an average dose of 6.3212 times 10 to the 14 atoms per square centimeter. A closed form confirms both numbers. Let us pull the chapter together. Partial derivatives represent the rate of change of a multivariable function with respect to each variable, computed by holding the others fixed. Assembling them gives the total differential, the first-order change of f when every variable moves at once, with a remainder of second order. And dividing that by dt gives the chain rule, which differentiates along a path and underlies both line integrals and backpropagation. Collecting the partial derivatives into a vector gives the gradient, which indicates the direction of steepest increase and is what optimization walks against. Constrained optimization problems can be solved using Lagrange multipliers, and multiple integrals calculate accumulated quantities over regions, often simplified by polar coordinates, provided you keep the Jacobian factor. Next chapter, vector fields and differential operators, where the gradient is joined by divergence, curl, and the Laplacian. Welcome to Chapter 4 of Calculus and Vector Analysis, Vector Fields and Differential Operators. In the last chapter, the gradient appeared as a byproduct of collecting partial derivatives into a vector. In this chapter, that vector becomes the main object of study. We will look at fields, meaning quantities that vary from point to point across a region, and at the operators that interrogate them. There are 4 of these operators, and they are the vocabulary of physics: gradient, divergence, curl, and the Laplacian. Each of them is built from partial derivatives you already know how to compute, so nothing new has to be learned about differentiation. What is new is what each combination measures, and that is the part worth understanding rather than memorizing, because it is what lets you look at an equation in a physics paper and know roughly what it is saying. Start with the object. A function that associates one vector to each point in space is called a vector field. Written out, a 3-dimensional vector field has 3 component functions, one for each direction, and each of those components can depend on all 3 coordinates. Compare it with a scalar field, which attaches a single number to each point. A temperature distribution is a scalar field, a wind map is a vector field. The examples the source gives are the ones that matter in practice: the velocity field of a fluid, the electric field, and the magnetic field. There are 2 standard pictures of a vector field. A quiver plot draws a short arrow at each of a grid of points, showing direction and magnitude directly. A streamline plot instead draws the curves that the arrows are everywhere tangent to, which makes the overall flow pattern easier to see. 2 simple examples will carry us through the whole chapter, so it is worth fixing them in your mind now. The first is the field f equals x. Y at every point other than the origin the arrow points directly away from the origin, and it gets longer the further out you go. Everything streams outward, nothing circulates. The second is the field f equals minus y. X at every point other than the origin the arrow is perpendicular to the line joining the point to the origin, so the arrows form circles around the center. Everything circulates, nothing streams outward. Both fields vanish at the origin itself, so there is no arrow to draw there, only a dot. These 2 examples matter because they separate the 2 questions the operators are going to ask. One question is whether anything is being created or destroyed at a point. The other is whether anything is spinning at a point. The 2 examples answer those questions in opposite ways. The first operator is the gradient, which you have already met. The gradient of a scalar field phi is written with the nabla symbol and has the partial derivatives of phi as its components. Pay attention to the types involved, because this is the cleanest way to keep the 4 operators straight. The gradient takes in a scalar field, 1 number per point, and gives back a vector field, 1 arrow per point. The direction of that arrow is the direction in which phi increases most rapidly, and its length says how rapidly. There is a geometric consequence worth carrying. Because moving along a contour line leaves phi unchanged, the gradient has no component in that direction, so wherever the gradient is non-zero, it crosses the contour lines of the scalar field at right angles. At a critical point, the gradient is 0 and has no direction at all, so the statement simply does not apply there. If you ever draw a gradient field whose non-zero arrows are not perpendicular to the contours, you have made an error. The second operator is the divergence. The divergence of a vector field f is written nabla.f and equals the sum of the partial derivative of each component with respect to its own coordinate. Notice the types again. A vector field goes in and a scalar field comes out, so divergence gives back 1 number per point. What that number means is the strength of the source of the vector field at that point. Positive divergence means the point behaves as a source, with more flowing out than in, like a tap. Negative divergence means it behaves as a sink, like a drain. Zero divergence means that whatever flows in also flows out, so nothing accumulates. Applied to our diverging field, x and y, the 2 derivatives are each 1, so the divergence is 2 everywhere. Every point is a source. The third operator is the curl. Written nabla cross f in 3 dimensions, it takes a vector field and returns another vector field, whose components are differences of cross-partial derivatives. The mental picture is a tiny paddle wheel dropped into the flow. The curl measures the local tendency to rotate, and in 3 dimensions it points along the axis of that spin. Be careful with the magnitude, though. The curl is not the angular speed itself. For a rigid body rotation, the angular velocity vector is half the curl, which is why the field minus y, x has curl 2, while the flow turns at angular speed 1. In 2 dimensions, the picture simplifies considerably, because a paddle wheel in a plane can only spin about the axis perpendicular to that plane. So in 2 dimensions, the curl collapses to a single number, the partial derivative of fy with respect to x minus the partial derivative of fx with respect to y. That 2-dimensional version is the one we will compute, and it is also the quantity that will appear in Green's theorem next chapter. Now apply both operators to both examples, and the table almost writes itself. For the diverging field x, y the divergence is 2 and the curl is 0. It has a source at every point and no spin anywhere. For the rotating field minus y, x the divergence is 0 and the curl is 2. It spins everywhere and creates nothing. The numerical calculations in the source, using central differences in each variable, reproduce those analytical values. The lesson is not the 4 numbers but their arrangement. Divergence and curl are asking independent questions, so a field can have one, both, or neither. Our 2 examples happen to isolate the 2 properties, which is exactly why they are the standard teaching pair, but a general field will have both a source part and a rotational part mixed together. The fourth operator combines two of the others. The Laplacian of a scalar field phi is the divergence of its gradient, and written out, it is the sum of the unmixed second partial derivatives. Scalar in, scalar out. Intuitively, it compares the value of phi at a point with the average of its neighbors, which is why it appears in many physical laws, including the heat equation and the wave equation. Both describe a quantity being pulled toward the local average of its surroundings. Two test cases show the range of behavior. For phi equal to x squared plus y squared, a bowl, the Laplacian is 4 everywhere. The center sits below its neighbors. For phi equal to x squared minus y squared, a saddle, the curvature in x cancels the curvature in y, and the Laplacian is 0. A field with 0 Laplacian solves the Laplace equation and is called harmonic. Now a theorem, and it comes with a hypothesis that deserves more attention than it usually gets. On a simply connected domain, meaning a region with no holes, such as all of three-dimensional space or a ball, the condition for a vector field F to be conservative, that is, for a scalar potential to exist, is that the curl of F is 0. In that case, F can be expressed as the gradient of the potential. This is a genuinely useful reduction. Instead of tracking 3 component functions, you track one scalar. Gravitational and electrostatic fields are the standard physical examples, but read the statement again and notice how much work the phrase simply connected is doing. The source is explicit that this hypothesis is essential, and the next slide shows exactly what goes wrong without it. Here is the counterexample. Take the field whose components are minus y over x squared plus y squared and x over x squared plus y squared. It is undefined at the origin, so its domain is the plane with the origin removed, which is a region with a hole. Compute the curl anywhere on that domain and you get 0. Every local test for conservativeness passes. And yet the loop integral of this field around any loop enclosing the origin equals 2 pi, not 0, so no single-valued potential exists. Going once around the hole changes the would-be potential by 2 pi. The precise statement to remember is the one the source gives. 0 curl is always necessary, but on a domain with a hole it is not sufficient. Topology of the domain, not just local behavior, decides the answer. When the conditions do hold, finding the potential is a mechanical procedure. Take the field F equal to 2xy, and x squared plus 2y first compute the curl. The partial of the second component with respect to x is 2x, the partial of the first with respect to y is also 2x, and the difference is 0, so the field is conservative. Second, integrate the first component with respect to x, giving x squared y plus an unknown function of y alone. Third, differentiate that with respect to y and match it against the second component, which leaves 2y fourth, integrate to get y squared. So the potential is x squared y plus y squared. And then verify, honestly. The source computes both residuals and checks that they simplify to exactly 0, rather than printing a checkmark the code never actually tested. Here is where these operators earn their keep in materials science. Fick's first law states that the diffusion flux, J equals minus d times the gradient of the concentration C. Read it term by term. The gradient of the concentration is a vector field pointing toward higher concentration. The minus sign reverses it, so the flux runs down the gradient from high concentration to low, which is exactly what diffusion does. And d is the diffusion coefficient, setting the scale. Take a concentration that is a Gaussian bump, highest at the origin and decaying outward. Its gradient points inward toward the peak, so the flux points outward, away from the peak. Then take the divergence of that flux, and you get a scalar field telling you at which points material is accumulating and at which it is draining away. At the center of the bump, the divergence of the flux is positive, 3.696405 on the numerical grid, and exactly 4. Positive divergence means net outflow, so more material leaves the region around the peak than arrives, and the concentration at the center falls. That is exactly what a Gaussian bump does as it spreads out. The source computes that divergence numerically on a grid, and the result is worth dwelling on. At the center of the grid, with a spacing h of 0.2, the numerical divergence of the flux comes out as 3.696405. The exact value, obtained from minus d times the Laplacian of the concentration, is 4.000000. The discretization error is 3.04 times 10 to the minus 1, a gap of about 7.6%. That gap is not a bug. Applying a numerical gradient routine twice builds a wide second difference stencil spaced 4h apart, and its truncation error at this spacing is exactly this size. Having h roughly quarters the error. The habit the source draws from this is the important part. Always print an exact or reference value next to a numerical one. Otherwise, there is no way to tell a discretization error from a coding error. Let us pull the chapter together. Vector fields associate a vector to each point in space, representing things like fluid velocity and electric fields. The gradient turns a scalar field into a vector field pointing in the direction of steepest increase, and wherever it is non-zero, its arrows cross contours at right angles. Divergence represents the source strength of a vector field, and curl represents its vortex. Our two standard examples isolate one property each. The Laplacian, the divergence of the gradient, is an important operator describing diffusion and wave phenomena. In conservative fields, the curl is zero and a potential function exists, provided the domain is simply connected, and the punctured plane shows what happens when it is not. Next chapter. Line integrals, surface integrals, and the three integral theorems, Green, Gauss, and Stokes, which tie divergence and curl to what happens on a boundary. Welcome to Chapter 5 of Calculus and Vector Analysis, the final chapter, Line integrals, surface integrals, and integral theorems. Everything so far has been preparation for this. We have integrals from Chapter 2. We have vector fields and the operators that probe them from Chapter 4. Now we put them together and integrate a field along a curve and across a surface. And then we arrive at the three theorems that make vector calculus worth learning: Green's theorem, Gauss's divergence theorem, and Stokes' theorem. Each one says, in its own dimension, that an integral taken over the boundary of a region equals an integral of a derivative taken over the interior. For Gauss's theorem, the boundary integral is a flux through a closed surface. For Green's and Stokes' theorems, it is a circulation around a closed curve. That single idea is why a physicist can write down a conservation law without solving anything, and it is the destination of this series. Start with the simpler of the two line integrals. Suppose a scalar field f is defined in space and a curve c runs through it. The line integral of f along c accumulates the values of f, weighted by how much curve there is. To compute it, describe the curve by a parameter t running from a to b, so that the position vector r of t traces out c, then the integral of f along c equals the integral from a to b of f evaluated on the curve, times the magnitude of r prime of t, that last factor is the speed. It converts a step in the parameter into an actual length along the curve. Forget it, and you are integrating with respect to the parameter rather than arc length. So the answer would depend on how you chose to parametrize the curve, which a geometric quantity must not. Now the version that matters most in physics. If the field is a vector field f, we integrate f dotted with the differential displacement d, r along the curve. Written in parameter form, that is the integral from a to b of f evaluated on the curve. Dotted with r prime of t, the dot product is doing the essential work here. It extracts only the component of the field that lies along the direction of travel and discards anything pointing across the path. So a field pushing sideways as you walk contributes nothing at all. In mechanics, this is exactly the work done by a force along a path, which is where the interpretation comes from. And notice one consequence of the dot product. Reversing the direction of travel reverses r prime, which flips the sign of the whole answer. Let us do both on the same path, the upper half of the unit circle, with x equal to cosine of t and y equal to sine of t as t runs from 0 to pi. First, the scalar field f equal to x squared plus y squared. On the unit circle, that quantity is 1 everywhere, and the speed is also 1, so the integrand is just 1 and the value is the length of the path, which is pi. Now the vector field f equal to y minus x. Its dot product with the velocity works out to minus sine squared minus cosine squared, which is minus 1 at every point. So the work integral is minus pi. The field opposes the direction of travel everywhere along this path, which is exactly what a negative work value means. Now the first of the three theorems. Green's theorem says that for a region D in the plane with boundary curve C, the loop integral around C of p dx plus q dy equals the double integral over d of the partial of q with respect to x, minus the partial of p with respect to y. Look at what is on each side. On the left is an integral around the boundary only. On the right is an integral over everything inside. And look at the integrand on the right. It is exactly the two-dimensional curl we defined last chapter. So the theorem says the total swirl inside a region equals the circulation around its rim. There is an orientation condition. The boundary must be traversed counterclockwise. Traverse it the other way, and, as we just saw, the left-hand side changes sign. Let us test it on the unit disk with the two fields from last chapter. First, the field f equal to x, why its two-dimensional curl is identically 0, so the right-hand side is 0, and the line integral around the circle also comes out as 0. The difference is exactly 0. Now the more interesting field, f equal to minus y, x its curl is 2 everywhere, so the double integral is 2 times the area of the unit disk, which is 2 pi. The line integral around the circle gives 6.283185, and the double integral gives 6.283185, with an error of 8.88 times 10 to the minus 16. What makes this a real test is that both sides were genuinely computed, one along the circle and one over the disk, so the agreement is evidence rather than an assertion. Move up a dimension. There are two things you can integrate over a surface S if you have a scalar field f. The surface integral of f over s accumulates its values over the area, which is the direct analog of the scalar line integral. If you have a vector field f, the useful quantity is the integral of f dotted with the unit normal n over the surface. That is called the flux, and it measures how much of the field passes through the surface rather than sliding along it. Notice that the flux needs a unit normal vector at every point, which means the surface must have a consistent choice of side. In practice, you parametrize the surface with two parameters, and a Jacobian factor converts steps in those parameters into real area, exactly as the factor r did for polar coordinates in Chapter 3. Here is a worked case on the unit sphere. Parametrize it the standard way. X equals sine theta cosine phi, y equals sine theta sine phi, and z equals cosine theta, with theta running from 0 to pi and phi from 0 to 2 pi. The Jacobian for the unit sphere gives a surface element of sine theta, d phi, and that sine theta is the factor that shrinks the patches as you approach the poles. Now integrate the scalar field f equal to z over the whole sphere. The answer is 0 by symmetry. Every patch in the northern hemisphere is matched by a mirror patch in the south where z has the opposite sign, and the two cancel. That makes it a cheap but effective test case, because the exact answer is 0, and you know it in advance. A correct routine will still return a small non-zero number because of rounding and quadrature error, so judge the result against a tolerance rather than against literal 0. A value well outside that tolerance points to a problem in the parametrization, the integrand, the Jacobian, the limits, or the quadrature settings. Now the second theorem, and the one with the most physical mileage. For a closed surface S enclosing a region V, with n the outward unit normal, the flux of f through S equals the triple integral over V of the divergence of f in words. What crosses the closed surface equals what the sources inside produce. That is a very satisfying statement, because it takes the local quantity we defined last chapter, divergence as source strength, and turns it into a global accounting identity. Surface integrals can therefore be converted into volume integrals, and in practice, one of the two sides is usually far easier. Read the orientation clause carefully, because it is part of the theorem rather than a convention. N is the outward normal, and choosing the inward normal flips the sign of the left-hand side. Test it on the unit ball with the field f equal to x, y, z, the three-dimensional version of our diverging field. The right-hand side is easy in closed form. The divergence of that field is 3, and 3 times the volume of the unit ball gives 4 pi. The left-hand side is computed numerically over the sphere. On the unit sphere, the outward unit normal is the position vector itself, so f dotted with n equals x squared plus y squared plus z squared, which is 1 on the surface. Integrating that with the surface element gives 12.566371, matching the analytic right-hand side exactly, with an estimated quadrature error of 1.4 times 10 to the minus 13. That number is 4 pi, and the left side really was integrated over the surface rather than assign the answer. The third theorem generalizes Green's theorem out of the plane. For a surface S in 3 dimensions with boundary curve C, the loop integral of f around C equals the surface integral over S of the curl of f dotted with the unit normal. So circulation around the rim equals total swirl through the surface. It is the three-dimensional version of Green's theorem, and if you flatten the surface into the plane, you recover Green exactly. Once again, orientation is part of the statement, and here it is the right-hand rule. Curl the fingers of your right hand along C and your thumb points along N, reversing either the traversal of C or the choice of N flips the sign. There is also a striking consequence. The right-hand side depends only on the rim, so any surface with the same boundary gives the same answer. Test it with the field f equal to minus y, x, 0, and let the surface be the upper hemisphere of the unit sphere, whose boundary is the unit circle in the plane z equals 0. The left-hand side is a line integral around that circle, and the integrand works out to 1 at every point, so the value is 2 pi, 6.283185. For the right-hand side, the curl of this field is the constant vector 0, 0, 2. Integrating it against the normal over the hemisphere gives 2 times the projected area, so the answer is again 2 pi. Both sides equal 2 pi. And this is where the earlier remark pays off. We could have stretched a flat disk across the same rim instead of a hemisphere, and the answer would not change. Step back and look at the 3 results side by side, because they are one idea wearing 3 costumes. Green's theorem, in 2 dimensions, trades a line integral around a closed curve for a double integral over the region it encloses. Gauss's divergence theorem, in 3 dimensions, trades the flux through a closed surface for a volume integral of the divergence. Stokes' theorem, also in 3 dimensions, trades a line integral around a closed curve for a surface integral of the curl. In every case, an integral over a boundary is exchanged for an integral of a derivative over what that boundary encloses. Once you see it that way, the fundamental theorem of calculus from Chapter 2 joins the family as the one-dimensional member. The boundary of an interval is just its 2 endpoints, and the integral over that boundary is a subtraction. Here is the payoff in materials science. Consider atoms diffusing through a solid. Take any region and observe that the amount of material inside it can change only by what crosses its boundary, plus whatever is generated inside. That boundary term is a flux integral, so the divergence theorem converts it into a volume integral of the divergence of the flux. Now both sides are volume integrals over the same arbitrary region, and if 2 volume integrals agree over every region, their integrands must agree pointwise. What drops out is the conservation law. The rate of change of the concentration C equals minus the divergence of the flux J, plus a generation term S substituting Fick's first law from last chapter, with J equal to minus D times the gradient of C, turns that into the diffusion equation. Finally, let us solve that equation numerically in 1 dimension, and, in the spirit of this series, check the answer against something independent. The scheme is explicit Euler, stable only while d times dt over dx squared stays at or below 0.5. Here it is 0.098, so the run is safe. Starting from a Gaussian profile with an initial peak of 0.9949, the simulation gives a peak of 0.7436 at t equal to 1.00, a decrease of 25.3%. Now the crosscheck. The initial profile is itself a diffused Gaussian, so the analytic peak decay is the square root of t0 over t0 plus t, which predicts a 25.5% decrease at that time. The two agree within 0.2 percentage points, the residual being the explicit Euler discretization error. Let us close the chapter and the series. Line integrals calculate accumulated values along a path for scalar fields and work for vector fields. Surface integrals calculate accumulated values on surfaces and flux for vector fields. Green's theorem converts line integrals to double integrals in 2 dimensions. Gauss's divergence theorem converts surface integrals to volume integrals in 3, and Stokes' theorem converts line integrals to surface integrals as the 3-dimensional version of Green. In materials science, these are applied to diffusion flux and conservation laws. Looking back across the series, Chapter 1 built differentiation and its numerical forms, Chapter 2 did the same for integration, Chapter 3 opened both up to several variables and gave us the total differential, the chain rule and the gradient. Chapter 4 turned the gradient into a family of operators on fields, and this chapter tied those operators to boundaries. Thank you for working through it.